This lesson is going to review exponential functions. When we talk about exponential function, this is something you've been exposed to in the past. The parent function, f of x, equals b raised to the power of x. We can look at functions and tell what type they are by where different exponents are and what powers the exponents may have. So in this particular one, exponential functions are defined by an equation of the form y equals a times b raised to the x. If b is greater than 1, the function is exponential growth. So we can think about germs growing, or if we had a very good bank account, maybe our money growing. We would love it to grow exponentially. And that is showing us that something's increasing. If b is greater than 0, but less than 1, it is exponential decay. And that is telling us that something is decreasing. So that example might be if we were trying to kill cancer cells and someone was taking chemo, we would want it to decrease rapidly. Now, in exponential functions, you have what's called an asymptote. And these are usually horizontal. They can be in different places depending on the transformation. But what an asymptote is a line. And we can graph that line with a dotted line when we're graphing, which the graph gets close to. It gets really, really close, and sometimes on Desmos it's very hard to even see that it gets so close, but it doesn't ever touch the line. So it gets close to the line, but never crosses it or touches it. All right, so the first section we're going to talk about is being able to plot an exponential function, whether it's growth or decay, being able to identify that, make a table, and then be able to identify some key features. So we look at this first graph, and we see that it has a number that is bigger than 1, so that's our base. That tells us that it is actually going to be growing. So we know it's a growth. And we're going to go ahead and pick a few points to put in our table to evaluate to see what y is worth. So when we plug the negative 2 in, 2 times raised to the negative 2 power, remember that with your exponent rules, when you have something to a negative, it's not very happy. So that's the same thing as saying 1 over 2 to the second, which is 1/4. So we have 1/4, then we have a half, a 1, a 2, 4, and I did an extra point down here just so I'd have enough to graph. So first thing we want to do is looking to see where our very first intercept is. That's usually a good place to start. So 0, 1, go with very easy numbers because if these little fractions, obviously we can't figure them out very well. So 1, 2, 2, 4, and 3, 8. And then we'll come over to the other side. We have negative 1.5. So we kind of have to just eyeball where that is. And then a negative 2 1/4. That's even closer. And then we'll connect our line and kind of make our curve. Now you can't make, in Desmos, these little arrows on the end, but they do go on forever and ever. So now that we have that graph, let's take a look at some important features. So if we look at our domains are our x values. So in this case, we have negative over here, negative infinity, positive infinity. And so these would go on forever for negative infinity and would go over forever for positive infinity. So this is all real numbers. We could write it as all real numbers. We could write it with the little notation of the r, or we can write it in function notation. Negative infinity to positive infinity with our parentheses. Now, if we look at our range, we're looking at where it approaches but never crosses. So we're really looking for our horizontal, or our asymptote, a horizontal asymptote. And so I'm going to look and see, I know it's getting closer and closer to 0, so it's getting closer and closer to the x-axis right here, but it's never going to cross that. So that's actually our smallest range. So we can think of our range as y being greater than 0, or in notation we could write it 0 to positive infinity. Now, let's go ahead and fill some other things that we know. We know our asymptote already. We know it's at 0. And so we write that as an equation, y equals 0. And our y-intercept, very easy to spot there. We also can spot it in our table. That is anytime x is 0. So we have 0, 1, and that is a coordinate. Now let's talk about end behavior. End behavior is something that is telling us kind of overall what's going to happen to the graph as it proceeds and goes the way it's going. So if we think about x approaching to the positive infinity, so x is our line in the middle, our axis in the middle, and we're talking about going towards the right. So when we're moving towards the right, our x is going towards positive infinity. What is our f of x doing or our y doing? Well, in this case, it is moving up forever, so that means it is approaching positive infinity. As we move to the left, looking at our x's, so as x approaches negative infinity, so we're looking here, what are the y's doing? Well, the y goes all the way down, but he never hits 0, so he's approaching 0. Okay, so that's our steps. Pause and try to do the next one, and then come back and see how you did. Now, if you take a look here, we notice that this one is actually decaying. It starts up high, and then it moves as we go left to right, it goes down. So this gives us an idea by looking at the graph, it's decay. If we look at the equation, we see that in the growth area, the growth factor, the 1/2, or the base, is smaller than 1, so that tells us it's decaying, but bigger than 0. If it wasn't 0, it wouldn't have anything. And it can't be 1, if we remember that from previous courses. We made a table, plotted our points. I made a little yellow highlighted line here for my asymptote, and I can see that it approaches 0, but it never fully crosses it. So my asymptote is y equals 0, so we have this here. Our y-intercept, 0, 1 as a coordinate. We already know decay. Our domain, again, goes negative infinity to positive infinity. And then our range starts at 0, not included, and goes positive infinity when we think about our y's continuing. So when we look at our end behavior, as x approaches positive infinity, y approaches 0. That's where it's approaching the asymptote. Notice the difference between the first one we did and the second one. They had the same asymptote, but one was growing and one was decaying. So it switches the end behaviors, and it also switches the way the graph looks, obviously. And then as we approach negative infinity, f of x approaches positive infinity. Now, we're going to move on to transformations of exponential functions. We've talked about this previously, so hopefully most of this rings true to you. And then we're going to identify some key features and some exponential graphs. So as we've learned before, with transformation functions, we have any type of parent function has its transformation equation where it kind of puts in where the h and the k would be, and if anything would change it for vertical stretch and horizontal and compression and all the fun stuff that we love. So in this particular transformation, as always, the h is the horizontal shift, so left and right. So if it's positive, it's going to shift left, negative is going to shift right. Notice where the h is here, okay? And then the vertical shift is what moves it up and down. So we know part of the formula is plus, so we can look exactly what it is. Now with the h, because negative is part of the formula, we have to think about what was put in there to keep the sign. So that's always a little sticking point for some of us. The a is going to give us something with compression or stretch vertically. Now, the h also can work in conjunction with the a, and we'll see that in some examples. So the first one we have is a function f of x equals 2x plus 5, or raised to x plus 5. So notice what these are. So we have a base of 2, we have the x value, and then we have a horizontal, or an h, shift, and it's a positive in there. And when we see positive, we know it's shifting left. So this shifted 5 units left, having a base of 2. So we originally, at the very beginning, actually had a graph that was 2 to the x, was our very first example. And this one is the same thing, but then now it's been shifted over. So if we look here first, we need to find a few important things. We need to talk about its domain. Well, this would go on forever and ever, so I don't have arrows here, but I'm going to put them just so you can see. And this was just graphed on Desmos, and I marked some key features. So we can look and say, well, that's going from negative infinity to positive infinity. Great. The range, think about what it's getting really, really close to. So that's where our asymptote comes in. So I'm going to put a little line right there. It's getting really, really close to y equals 0. So that's our asymptote, so we already know that, so we can go ahead and write that. So y equals 0. We also can look and say, okay, well then the range has to be bigger than 0, so 0, not included, can go forever to positive infinity. We also could write that as y is greater than 0. Now, with our end behavior, we have as x approaches positive infinity, so that's moving this direction. So we're going that direction, and we want to know what is happening to the value of the y's. Well, the y's are going up, so they're doing positive infinity. When it's approaching negative infinity, what is happening to the y's? Well, they are going as close as they can, but they're getting to 0, and then they're stopping. They can't go any further that way, so they're getting to 0. Now, notice on this graph, we cannot see exactly where the y-intercept is, but remember, y-intercept is always when the x value is 0. So we can easily plug in to our formula 0 for the x plus 5. So we end up with 0 plus 5 is 5. So that is 2 to the 5th. And if we remember our exponent rules, 2 to the 5th gives us 32. So we know that our y-intercept is 0, 32. Now, you have a few more that I want you to try. Pause the video, then come back and check, see how you did. All right, let's take a look and see how you did. For number 4, I marked our horizontal asymptote at y equals 2, so that gives us pretty easy to see. I want you to kind of make the connection here. If we look at what pieces that we have our base here, that's our b. So we kind of know that that's our factor, that's how things are multiplying to get bigger. And then we have attached out here to the side, not with the h, but out to the side, in the k spot, we have a negative 2. Notice that our asymptote is also negative 2. Those are connected, so pay attention to that. And then notice how that changes our range. Our range was changed to start here at negative 2 and go to infinity. Also, our end behavior for our x approaches positive infinity to what does y do also changed. So those have a big impact on things. Y-intercept, very straightforward. Number 5, we have a little bit more pieces here. Here, this half is not a growth factor, or it's not the base. This is actually the A. This is to deal with the stretch or the compression. And we know that if it's smaller, what happens? So then we look here and we see in our K spot, we have a positive 1. Notice that our asymptote is also y equals 1, how they're connected. Then notice our y-intercept is 0, 1.5. Well, notice what our A is. It's a half, which is the same as 1.5. That's also a value that gives us, that gives us the y-intercept. So the A is our starting point as well. So make sure you understand those connections. And then pay attention to what has happened to the end behavior and the domain and range. Notice with all of these that we've done so far, our domain and range hasn't changed. Okay, so that tells you a little bit about those. So let's go to our last one. This one is a little different. And we look at that first and we think maybe it's decaying. But this has been reflected over the x-axis. If I took away the negative sign here, which is what caused it to reflect, it would be doing something like here. So when we think about that, we think about it's growing. It's growing, but it's just reflected over. So that kind of helps us kind of see what's happening. That reflection helps us go over. The 2 is the initial. It also kind of tells us where things are hitting. This one's a little different though, because normally we say, oh, well, that A, that's where our initial is, our y-intercept. But notice it is not. Our y-intercept is not there. Our y-intercept is at 0, negative 0.125. So we'll have to think, how do we get that? And we're going to see that in just a few minutes. And then here, now we have an h value. And we haven't seen many of those yet, but we have no k. So the k, because there's nothing here, it's like a plus 0, that gives us our asymptote. So pay attention and start paying attention to those connections. Also, look at this, how this range changed. We started negative infinity to 0 instead of the other way around with the other ones. Now, we're going to move on to talk about how to create exponential equations without a calculator when you're given just the graph. Now, in this step, I would suggest writing down these steps, really understanding how you do them, because doing this without a calculator takes a little bit of practice. So the very first thing is we want to identify key points. And key points are things that we can clearly see, nice, good points, like y-intercepts, another point that's clearly on the graph. I like to look at the horizontal asymptote. That gives me that k, remember, where it's approaching. That's an easy thing to find. I like to look what points would have x values of like -1, 0, and 1, because they're very easy to plug in and help me solve other things. Pay attention to what type of pattern you see. Growth, decay, if it's reflected, that'll tell you a lot about what the a should be. Obviously, if it's growing, that number has to be bigger than 1. If it is decaying, it's going to be a fraction. And if it's reflected, you're going to have a negative in front of that. So we're going to create a couple helper equations to help us. So the first one we're going to create after finding our key points is one that we're going to use, and we're going to treat the h like a 0. So we're using this equation here. That's our transformation equation to plug things in. But we're going to treat h like it's a 0 in these. And they'll make more sense at the end, because vertical stretch and horizontal, they work together. They actually undo each other. So it can become very cumbersome if we try to put something in there. We don't know what they are right now, so we're going to treat it as 0. So we're going to try to find the y-intercept for each of ours, the k, and then we're going to use that to make an equation to first solve for a. Once we solve for a, then we'll put back in another equation, and we'll solve using now our new a term, and we'll solve for b. Preferably, we like to use the other point when x is 1. And then we're going to rewrite our equation just in this form here without the h. And then we're going to look and see what type of relationships that a and b may have that we can make it a little nicer and a little more detailed. So I'm going to start with the first one. I made some kind of quick notes of things that I'd like to have. So I kind of looked, yes, their growth. For number 7, it's growth. I want the y-intercept, so I'm going to look on my graph, and I can see, and you can zoom into these a little bit, make this a little bit bigger for you to see. I can see that my y-intercept is 0, 4. So I'm going to go ahead and write it there, 0, 4. I want another point that is preferably when x is 1. So x is 1 right there. So when I go up, there's a nice clean point. That is 1 and 8. Now, if I can't get that, I can look for a -1. -1 here, actually, it's not bad. -1 and 2. So there's another point for us. Now, let's go ahead and see if we can find our horizontal asymptote. So when we look at our line here, we can see that it's coming close, but never crossing y equals 0. So that is going to be our k, which will be 0. So you can think about your y equals 0, that's your k, that's your asymptote. Now, our a is our initial. It's exactly where things are, but we can't always go with that when we are first looking at things, but we can try it. So we think that a should be 4, because that's our initial, that's our y-intercept, that's where it's starting. And notice what our asymptote is, and that'll kind of help you see that later. But we're going to pretend like we don't really know that right now, and we're going to start with plugging in. So we're going to plug in first where h is 0, we know k, and we know the y-intercept. So we're going to use the y-intercept in our formula. So we're going to plug into y equals ab to the x plus k, and we're using our y-intercept. So we have when y is 4, we don't know a yet, but b, we don't know, would be raised to the 0, and then we know that our k is 0. Well, the 0 doesn't really matter. We can get that away. And anytime we raise any number to the power of 0, it is worth 1. So we end up with 4 equals a times 1, which gives us a means 4. Well, we already kind of knew that. but now we have proof. So now we're going to make a second equation. I'll make a little line here. And this time we're going to use another point. We're going to use this point where it's 1 and 8. We could use the negative 1 and 2, but I like to have the x values be a 1 of some kind, preferably a positive. So we're going to then plug in when y is 8. A we now know is 4. B is what we're trying to find, raised to the first power. And we don't have a k, so there's no reason to put a plus 0 out there. So we're going to simplify. Well, b to the 1 power is just b, so we end up with 4b is equal to 8, and we divide by 4, we get b is equal to 2. So now we know these pieces. So now we're going to rewrite them in our step D here. We're going to rewrite them in the form we know. So y equals, we know that a is 4, b is 2, replace our x, and we don't need to put plus 0 because we don't know. So this would match this graph. If we put it into Desmos and matched it up, it would match. But we want to see what really happened to move this. Did this move left or right? Did this move up and down? When we look at this, we're just thinking, oh, well, it had a vertical stretch of 4. And while that may be true, because whatever it does, H undoes, and they work together, kind of opposite of each other, let's look at these pieces right here and think, is there any way to rewrite that 4 as a base of 2? Well, I know that 2 raised to the second power is also 4. So if we remember our rules of when we multiply same bases, what we do with the exponent is we keep the base and we add the exponents. So x plus 2. So our problem can be written as a function of f of x equals 2 raised to the x plus 2. This equation and this equation are equivalent, but this second one with our h tells us a little bit more of what's happening, and it's in a different format when they're asking about moving left to right. So this is a little bit higher advanced. I want you to get to this point. So I want you to try number 8 and then come back and see how you did. Now, for number 8, I did all my steps here. I plugged in. I actually found an extra point there, and I found my k, my asymptote. If I look right where it approaches, it's at 1, okay? I found a y-intercept where it was at 1 when x is 1, and then negative 1 as well. One thing we didn't do in the first one is plug a point back in to actually make sure it works. So we have to always make sure we do that so we know if we actually got the right equation. So when I worked, I found 4 is a, and then b is a half. Plugged it back in with my k value of 1, and I get 4 times half raised to the x plus 1. So I want to look at my a and my b. I can't change the b. That's my factor. That's my base. It's not changing. It is what it is. That's how the multiplier is happening. But is there any way that I can write 4 as a base of a half? So if I think about writing a half, what could I raise it to get it to be 4? So that's where we could actually have a negative 2 exponent. So remember that when we have negative exponents, they're applied to each piece. So we'd have a negative 2 and 2 to the negative 2. And they're not happy with negatives, so we move them to the basement or move them to the top of the house. So this is the same thing as saying 2 to the second power and 1 to the second power. And we know that 1 to the second is 1 and 2 to the second is 4, so it does get us back to 4. So when we look at our rules of bases with exponents, we have like bases, which is a half, and we add the exponents. So x minus 2, and then we put our 1 out there for our k, and we are going to go ahead and write our function notation. Make myself a little bit of room here. So we have f of x equals this equation. Now, I pulled another point, that negative 1, 9, out of here. So to check myself, I can plug that point in. I can put in a negative 1 for my x. So I would have a half, a negative 1, and a negative 2, and plus 1, and that should equal 9. So a negative 1 and a negative 2 gives me a negative 3. Well, that would be a half to the negative 3, which would mean that I'd have 1 to the third and 2 to the third. Well, 2 to the third is 2 times 2 is 4. 4 times 2 is, hope you said it, 8. And then we would add the 1, and it would equal 9. So then we know that we have the correct equation. All right, let's do one more that's a little bit more complex. And I'm going to let you try this one. All right, so let's take a look at number 9. We know it's a growth. We found all our pieces, plugged them in. And at the end, we got 2 as our A, 2 as our B, and -1 as our K, which is also our horizontal asymptote. And then we looked and said, can we rewrite 2 and 2? They have the same base. We just looked a little bit more clearly and said, well, that's raised to the 1. So we kept those bases and we add the exponent. So we got 2 raised to the power of x plus 1 minus 1. We can take another point like this -1 and 0 in there and plug it in. Well, if I put in -1 where the x is, -1 plus +1 is 0. 2 raised to the 0 power. Anything raised to 0 power is always going to give me 1. 1 minus 1 is 0. So yes, this does work, and this would be our answer. All right, the last one is we can see that it's reflected, so we know the A is going to be negative. We also can see our horizontal asymptote. It comes very, very close, but it never touches or crosses that line there, and that is going to be where y is -1, so that gives us our K. So we're going to go ahead and plug in what we have. So we're going to start with using the y-intercept. So when y is -3, we don't know A, and we're going to then plug in b raised to the 0, and then we'll use our K, so -1. Well, b raised to the 0 is always 1, so we end up with -3 equals A minus 1. Move the 1 over, and we get -2 for our A. Notice if we would have just looked at the y-intercept, that is not correct because of things being reflected and shifted. So we can't just go with A is always our y-intercept. So this would give us a -2. Well, that makes sense. It's reflected, so it's got to be a negative number. And if we flipped it back over, we could see that it's growth. So it makes sense that it's a -2, not a fraction. So now we're going to use another point, preferably the one with the 1. So we have -5 would equal, we now know A, so -2. We don't know B. But we're going to raise it to the first power because 1 and -5 is what term I'm using, and then -1. And we're going to simplify. So when we simplify here, we're going to end up with -5 equals -2 because b to the 1 is just b. And then -1, move the 1 over, we get -4 equals -2b. And then divide, we're going to get b is equal to 2. Now, we have all our pieces, and now we're going to plug them in. So y equals A, -2, 2 raised to the x, and -1. And then you want to look at these exponents. The negative is going to stay. We know that's part of our final equation regardless. That tells us about the reflection. But remember, this is like 2 to the 1. So we keep our base, add our exponents, and then bring down our k. Now we can have, I put a k there instead of a 1, our 1. And we can have parentheses around there if we want, and then write it in function notation. Now we can take another point like the -1, 2, plug it in, -1 and a +1, give me 0. And then that is to our 2 power, and we would have, it would equal, -1, it would equal here. I put the wrong thing here. It's supposed to be a -2. Let's find it right there. -1, -2. Sorry about that.